and I'm going to be talking to you about brighter and hotter, a mechanism for heating the fourth state of matter, plasma. So imagine you're the Martian. You're marooned on Mars, over 200 million kilometers from home, and you've just run out of water. Fortunately for you, though, you're smarter than Matt Damon because you know there's liquid water on Mars. But once you have it, how do you know it doesn't contain toxic or even radioactive elements? My research at Trinity College centers around the enhancement of a technique that allows you to determine the elemental makeup of any sample, big or small, solid, liquid, or gas. This technique is known as laser-induced, breakdown spectroscopy, or just simply LIBS. In LIBS, a laser with the power equivalent of 1,100,000 watt light bulbs focused down to just 1 square centimeter is incident on a target. And what that does is it creates what is known as a plasma, a collection of electrons and ions. This plasma emits light or a spectrum, and the study of the spectrum is known as spectroscopy. Now, light or a spectrum is essentially a fingerprint. No two elements will produce the same spectra. However, some elements will produce similar spectra. Take, for instance, copper and boron. Copper and boron both produce a greenish spectrum at their burning temperature. But to tell them apart, we add energy to them, and copper will turn more blue while boron will turn more violet. The reason for this lies with the electrons interacting with a particular ion, and we can think of this interaction like unique stair steps. The more energy we give to the electrons, the higher up the stairs they can go. Once we give the electrons a particular amount of energy and they're at that particular stair step, they must come back down and they must emit light along the way. The more stairs they descend at once, the more towards blue light they'll emit. The fewer stairs, the more towards red light. Now, the way we put energy into a plasma is through the use of electric and magnetic fields. I use a time-varying magnetic field in my research to bring the particles very, very close together, confine them to a specific orbit, and also drive a current through them. Now, this kind of magnetic energy coupling we know and is similar to how wireless charging works. In wireless charging, we have a base station, which you're about to see, which is a coil producing a magnetic field. And you also have a receiver, which in my case is my plasma, which I drive a current through. On the top right, you see two images of a copper plasma. The top image shows a green copper plasma without any additional energy coupling, just expanding into free space. Whereas the bottom image, you see the effect that my device has, putting energy into the plasma, bringing out the hotter blue light, and also focusing the plasma, which tends to make the light last a little bit longer. Now, it's exciting to say that my research could one day benefit many fields, from here at home to well abroad. For instance, LIBS can be used in environmental monitoring to look at water, dirt, rock, soil, air samples in an effort to determine if there are any toxic or hazardous elements. LIBS can be used by museum curators to do depth profile analyses on artwork to see if a particular piece of artwork has been touched up or from a particular period or location. And finally, LIBS can be used abroad, well, on another planet. It's actually being used on Mars right now by the Mars Curiosity rover in an effort to determine elemental makeups of rock and soil samples and to piece together how a whole planet once appeared. Thank you.